Welcome to section 4.2. You're in for an easy day, and so nobody wants an easy day, so I want to make it less easy for you and remind you you need to be working on that practice midterm. It's super long. You cannot do it the night before, and you don't want to do it the night before. It's going to take, a week to do, and there's a lot of problems you can do right now, so I want you to get started on that. All right, let's start, before we do limits and continuity, with just a review of finding a level curve. And so here we're just told to find the level curve that passes through a certain point, but we're not given the value of C. So we have to find C on our own. C is f of -1, 1. Okay, and that would be 3 on top and 1 on the bottom. So C is 3. So that's step 1. Step 2 is to set f of xy equal to c, and that's the level curve. F of xy equal to 3, and this will give us the level curve. So f of xy is 2y minus x over x plus y plus 1, and we set that equal to 3. Okay, I can't even recognize that at this point, right? If you were to ask to graph that, you'd be like, well, not sure. So let's solve for y. Moving up here, multiply both sides by this denominator. So 2y minus x is 3x plus 3y plus 3. And let's see, I'll move the y over there. So I'll get y equals, and then I'll move all my x's to one side to give me -4x minus 3. Okay, I can graph that, and so can you. It's a line. Passes through -3 on the y-axis, and it's got slope -4. So let's just make a fairly steep negative slope. That's good enough for me. And this is the point 0, -3. Okay, on to the new stuff, kind of. I say kind of because the parametrization Bible you've seen before. You saw it in Math 1B. And so I'm just putting it here for your easy reference and to remind you of the 3 special types of functions that we it's so hard to say that word, parametrize frequently: line segments, circles, and functions. And so you can just use these formulas to get your parametrizations. We're not going to do a lot of parametrizing in this section, but later in the course we'll be finding parametric equations right, left, and center. So this isn't going to go away. So let's use these rules to do some simple parametrizations. Parameterize the following curves. The line y equals 3x. Okay, so don't use the one for line segments because that's a segment from one point to another. We want the whole line. This is actually falling under this category. It's a function y equals f of x. So our f of x is 3x. And so the parametrization Bible would say let x of t, y of t. And some people use pointy brackets. Some people use round brackets. There's really no one way to do it. And some people write 2 separate functions. They'll go x is t and y is f of t. Okay, I'm okay with any of those. But for this guy, I'm going to use pointy brackets because that's what I said to do here. So r of t, for functions it says let x be t and let y be f of t. So f of t is 3t. And then if I only wanted to go from one point to another, I would put limits on t, how far I wanted to go. I'd let t go from a to b. But I want the whole line, so I'm just going to leave it like that. It's that easy. This one usually gives people trouble because it's so easy, they think it can't possibly be that easy, but it is. Okay, next one, r of t. Again, it's a function y equals f of x, so t comma t squared. All right. And it's later in the course that we'll be putting restrictions on t. In this section, we really just need to get the parametrization. X-axis Okay, an equation for the x-axis is y equals 0. So again, this falls in category 3. R of t is x is t and y is 0. And you can see as t goes from negative infinity to infinity, you're going to get the whole x-axis. Okay, let me remind you how limits of functions of one variable work. When you're finding a limit and nothing bad happens, like you're not dividing by 0, you can simply take this number here, x equals 0, where you're taking the limit, and plug it in for x and get your answer, and that'll be your limit. So this is going to be 2 plus the square root of 25, which is 7. Nothing bad happened, so that's our limit. So that means as I'm coming in to 0 here on the x-axis, my y values are approaching 7. All right, well, the same thing's going to happen with a function of two variables, except now up above you got a surface, not a curve. And and one other thing, there are many ways to approach a point in the denominator. With one variable, you can just do a left-hand limit and a right-hand limit, but in a situation like this, there are infinitely many paths you can come in at to the point in question. However, the rule still is, if nothing bad happens, just do it. And so this is going to be 4 plus the square root of 9, which is 3, and so that's 7. So that's our limit up here. Now we all know that something bad's going to happen soon, and that would be on the next page. Here's the precise definition of limit. We're not going to use it in this class, but you will use it if you take an advanced analysis class. But pretty much it's very similar to the single variable definition. As long as you're close to your x naught, y naught down here, your z values want to be close to the purported limit up here on the z-axis. Limit laws. Don't memorize these. They're the same limit laws we have for functions of single variables. So let's just see how to use them. Here's our first example. We're going to go to pi over 2, pi over 4, and here's our function. And you know, with trig functions, oftentimes you have to do something fancy, but let's just check and see if anything bad happens, because if nothing bad happens, we can just plug the limit in. So let's see, cosine of pi over 2 is 0. Now, as long as we don't get a 0 in the denominator, we're going to be good. 2 minus sine of pi over 4 is 1 over root 2. And so I don't know what that number is, but I know it's not 0. So 0 over a non-zero number is 0. That's my limit. Nothing bad happened. Okay. Finally, something bad's going to happen. If I put 4 in for x and 4 in for y, I'm going to get 0 over 0, which is a do more work. So copy along the limit sign. And this is kind of a pain because when you copy along the limit sign, there's a lot more to write than just with the single variable. But I know you can do it. Let's factor an x out of the top. X minus y, root x minus root y. Now, with square roots, you typically want to be rationalizing, but there's a trick here I'm seeing that can help us avoid rationalizing. We can write x minus y as root x minus root y times root x plus root y. Limit, and just did this in my other calculus class, Math 1B. We were just doing this. Of course, we only had a limit with one variable, but it was the same idea. So let's write the top as root x minus root y, root x plus root y. Now, if you have to, pause the video and convince yourself that if you FOIL that out, you get x minus y. That's the nice thing about having video lectures. When I go too fast or when you don't understand something, you can just hit pause and the whole class doesn't wait. You can just pause it for as long as you want and figure it out. So it's kind of awesome. All right, kill. And this is the limit as xy goes to 4, 4 of x times root x plus root y. And now we're ready to take the limit because nothing bad's going to happen. 4 times root 4 is 2, 2 plus 2. So 4 times 4 is 16. There we go. Okay. Next one, very similar to the last one. Again, when you see the square root, you think knee-jerk reaction, rationalize, but in this case you don't have to because the bottom, like this 2 squared is 4, root x plus y squared is x plus y, so we can do the exact same thing we did up top. We can factor. By the way, this is a 0 over 0, and that's why I'm even bothering to do this. So this is the limit x, y, even I find writing this limit a pain, 2, 2. Okay, so let's factor the top as root x plus y minus 2 root x plus y plus 2 over root x plus root y minus 2. All right, so now these are common factors, so kill, and then the only thing that's left is the limit of this guy right here, and rather than write down the limit sign and what's left, I'm just going to take the limit if you'll allow me to do that. No, because I want to set a good example. Limit x, y. If I start making shortcuts, then you're going to start making shortcuts, and it's just better to teach you how to do it right to begin with. Okay, plus 2. Okay, so now we can take the limit. 2 plus 2 is 4. Square root of 4 is 2. 2 plus 2 is 4. Okay, last one. No square roots. But it's looking fishy because, 6 squared is 36 and 7 times 2 is 14. So let's see what we can do. Let's get that 6 out of the bottom and a 36 out of the top. So take a 36 out, and what I'm left with is x to the 14th minus y to the 14th. And if you'll allow me, I'm going to factor that as x to the 7th minus y to the 7th times x to the 7th plus y to the 7th. So again, pause if you feel that you're not quite getting that, but if you do FOIL, 7 plus 7 is 14, outside and inside terms cancel, and it's going to work. Downstairs, take out a 6, and we're just left with x to the 7 minus y to the 7. Kill. 6 goes into 36 6 times, so I'll just write the limit one more time. 6 x to the 7th plus y to the 7th. And then we can take the limit because nothing bad's going to happen. 6 times 2 is 12. All right. So now I had mentioned that there are many ways to come in when you're taking a limit of a function of two variables. There are many ways to come in at x naught, y naught on that domain. And so we can use that to our advantage. It seems like a disadvantage, but we can use it to our advantage, but only to show a limit doesn't exist. Okay, so this is called the path test. Suppose we have a curve in the domain, right? And we can specify the limit towards x naught, y naught. And we can say, I don't want to go, in any other direction except along that curve. I want to approach x naught, y naught, that's down here, along that curve. And so the way to do that is to parameterize the curve. That's why we had that little primer on parameterizing. Parameterize the curve, write everything in terms of t, and then you can replace this big limit as x, y goes to x naught, y naught along c with just the limit as t goes to t naught, as long as x naught, y naught is x of t, y of t. Usually it's going to be the origin, so that's not going to be an issue. So let me show you how that works before we show a limit doesn't exist. So rewrite the limit in terms of t. So we want to find the limit as x, y goes to 0, 0 along c of this function, and c is the curve y equals x squared. So the first step is to parameterize c. Parameterize c. R of t equals, well, this is a function, y equals f of x, so we're going to let x be t and y be t squared. Okay, then notice as x, y goes to 0, 0, that's the same as setting t equal to 0. So the second step is rewrite our limit. The limit, I'm going to replace x, y goes to 0, 0 with t goes to 0. And then up here, everywhere I see an x, I put in a t, because this is x. And everywhere I see a y, I put in a t squared. So that gives me t squared plus y is t squared, divide by y, which is t squared. Now, of course, don't try and cancel those t squareds because they don't cancel. Simplify the numerator. Limit as t goes to 0 of 2t squared over t squared. Kill, kill. Now that's the limit of a constant. Limit as t goes to 0 of the number 2, which is 2. And so there's a nice visualization up here. Here's the surface. Here's the curve y equals x squared. As I come in along y equals x squared, the value of my function is actually constantly 2. And so the limit is 2. All right, so that's how you find a limit along a curve, but how do you use that to show a limit doesn't exist? So that's my next topic here. Let me see how I'm doing on time. We're doing good. I think I can finish this all in one video rather than make 2 videos. So the idea is with a function of a single variable, if you can show the left-hand limit, would be left-hand limit, is not equal to the right-hand limit, then you showed the limit doesn't exist, because you need the left-hand limit to be equal to the right-hand limit. So left-hand limit is not equal to right-hand limit here. With a function of 2 variables, if you can find 2 curves where the limit along one curve is different than the limit along the other curve, then you could say the limit doesn't exist. Instead of left-hand limit, you'd have to say like the limit along C1 is not equal to the limit along C2, and that would prove that the limit doesn't exist. So this method doesn't prove a limit exists, it only proves one doesn't exist. And it's called the path test. If f of xy has 2 different limits along C1 and C2, then the limit doesn't exist. Pick easy paths. Don't make your life hard. What's easy? X-axis, y-axis, y equals x. Those are all easy. And I think in your homework, they even tell you what paths to choose. And I'm going to tell you also, so you don't have to figure it out yourself. And when you graph these on Calc 3D, crazy things happen. It's really hard to see what's happening, but you can tell that at the origin, something insane is happening. You're not getting a nice limit. So let's see. Use the paths y equals x and the x-axis. So first of all, y equals x. We have to parameterize that. Let x be t and y be t. That's the parameterization for the line y equals x. Now we're going to replace this limit with a limit just in terms of t. Limit is t goes to 0. Everywhere I see an x, I put in a t. Everywhere I see a y, I put in a t. So the top will give me t squared. And on the bottom, I'll have t squared plus t squared, which is the limit as t goes to 0 of t squared over 2t squared. You always want to simplify before you take the limit. Kill, limit as t goes to 0 of 1/2. All right, that's the limit of a constant, and so it doesn't matter where t is going. 1/2 just lives at 1/2, so that's a half. Okay, and if we want to show this limit doesn't exist, hopefully the limit along this other path will not be 1/2. So for the x-axis, I'm going to parameterize as t0 and replace the limit. T goes to 0. Everywhere I see an x, I put a t, and everywhere I see a y, I put a 0. So on top, I get 0, because 0 times t is 0. And on the bottom, I get what? T squared plus 0. Now, you might think, well, Dr. Gaynor, that's 0 over 0, right? Because as I let t go to 0, 0 over 0. But it's not, because you have to simplify before you take the limit. And so if we simplify 0 over t squared is some number. Granted, it's close to 0, but it's not 0. So 0 over some non-zero number is indeed 0. So you're not taking the limit of 0 over 0, you're taking the limit of 0, the good old number 0, which is 0. Okay, so we've just showed that this limit doesn't exist because the limit along y equals x was not equal to the limit along the x-axis. 0 is not a half, so we're good to go. Okay, 2 more topics. One is continuity, which is really nothing more than finding domains, which we've already talked about, and that's kind of fun. And then I thought I would do a primer on taking derivatives, because that's going to be coming up. And so I'll do some problems with you, but then I've got a whole section of practice derivatives that I took from Math 1A. It was like a practice test in Math 1A. And there's answers at the bottom. So I strongly suggest you do those, because if you can't take these derivatives, there's no way you're going to take derivatives with 2 variables. Okay, so we're going to take these derivatives and put them on steroids. So make sure you can do the non-steroidal version first. Okay. The definition of continuity is the same as it is for a function of 1 variable. You just add an extra variable. You need the limit as you approach a point of the function to be equal to the value of the function at that point. Describe and sketch possible set of, if possible, the set of points where f is continuous. So we really just need to find the domain. This function will be continuous on its domain. How do I spell domain? D-O-M, it's like 4 in the morning, A-I-N. All right, so remember the rule for logarithms. You take the argument out and you set it strictly greater than 0, because you can't take log of 0 and you can't take log of a negative number. So that gives me, let's move the y to the other side. Negative 6x is greater than y, which I like to write as y less than negative 6x. All right, so I'm missing a y there, huh? Y less than 6x. So y equals 6x is a line, goes through the origin, slope negative 6. Since there's a strictly less than here, I'm going to dot in that line because it's not part of the domain. Those points are not in the domain. And then what regions do I shade? Well, if I want y less than negative 6x, I want to be below that line. If I wanted greater, I'd be above, but I want to be less, so I'm going to go down there. So there's your domain, and it does not include that dotted line. If I wanted it to include the dotted line, if this had been a greater than or equal to, then that dotted line would be a solid line, but it's not. So take that away. Okay, one more. Homework asks you in this case to graph the set of points of discontinuity. I'm just going to graph the places where it's continuous. So we've got a fraction, and the rule for fractions is don't let the denominator be 0. So we need xy minus 1 not equal to 0. So we need xy not equal to 1, so we need y not equal to 1 over x. Okay, that's a hyperbola. Those are bad points. The points on y equal 1 over x are points not in the domain. So I'm going to dot those in. This is what y equals 1 over x looks like. Okay, now the domain's everything except those two dotted lines, because everything else is fine. So this is good, and all this is good. Okay, and I think if I'm remembering correctly, the homework is just going to ask you to sketch in the dotted lines. They're not going to ask you to fill in the places where the function is continuous. Okay. Last topic, just-in-time derivative reminders. We've got product rule, we've got quotient rule. You've got to memorize those. Power rule, typically we all know d by dx of like x to the 5th is 5x to the 4th, but the generalized power rule is for d by dx of some function to the 5th power. And in that case, you multiply by the derivative of the inside. So here's an example. I want d by dx of some function to the 9th power. So in this case, my u of x is x squared plus 3. So to take the derivative, I don't know if you remember from Math 1A, I had take the derivative of the mama and leave the baby fixed. The baby is the inside. That's the derivative of the mama. And then you multiply by the derivative of the baby. The baby is the x squared plus 3. So multiply by 2x. And of course, no one would leave an answer like that in third semester calc. You guys would all be like, oh, I got to clean that up. That's 18x times x squared plus 3 to the 8th power. Okay, and then I want to remind you about taking derivatives of trig functions. When you're taking the derivative of a trig function raised to a power, it's so much easier if you first rewrite it. So I'm not taking the derivative. That's why I have the d by dx here. The d by dx disappears once you take the derivative. But if you have to rewrite it, you got to keep the d by dx. This is cos 4x all cubed. And now mama baby is more obvious. Baby's cos 4x, mama is something to the 3rd power. So now I'm going to take the derivative, so I'm dropping the derivative sign. Bring the 3 down. Leave cos 4x fixed. New exponent's 2. Then I multiply by the derivative of cosine 4x, which is negative take the derivative of cos. There's another mama and baby here. Take the derivative of cos, which is negative sine. Leave the 4x fixed. That's the second baby. I guess it's twins. Then multiply by the derivative of this, which is 4. And so all together, the parentheses are really awkward here, and we can get rid of them by taking that negative and moving it out front. Negative 12 cosine squared. I'm going to put my exponent back over the cos. 4x sine 4x. No parentheses needed. Okay, natural log. We love taking derivatives of natural log. The rule is derivative of ln u is u prime over u. It's that easy. So the log disappears. There's no log in your answer. So I put my u on the bottom, x squared plus 1, and my u prime on the top. Piece of cake. Exponentials we love even more than logarithms because they're even easier. And the rule is copy down e to the u of x and then multiply by the derivative of the exponent. So it's not the power rule. So if you have the derivative of e to the 5x, you do not bring the 5x down and then subtract 1 from the exponent. I don't even like to write that. It's so bad. No, 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 no. That's the power rule that you use for x to the n. But exponentials, e, they have their own special set of rules. And this is the rule. You just copy down e to the u, multiply by u prime. And so this derivative, leave a space in front, e to the x squared, and in the front you multiply by the derivative of x squared, which is 2x. Finally, inverse trig, you do have to memorize these. The sine inverse, tangent inverse, secant inverse. The other three you'll get for free, like d by dx of cos inverse u of x. It's the exact same thing except with a minus on top. So minus u prime over the square root of 1 minus u squared. Cotangent, same thing, minus cosecant. But these are the three we use the most, so really you should focus on these three. So here's just one example, and then I'm going to call it a day. I'm using this formula right here. I want u prime on top, that's 6x. And on the bottom, I want 1 plus u squared. 1 plus 3x squared squared. And I really do need to know that you know how to simplify exponents at this point in your life. And so this is 1 plus 9. And then when you have an exponent to an exponent, you multiply the exponents. X to the 4th. Okay, so pretty easy day, but a lot of content. And I really strongly urge you to make sure you can take derivatives before we go any further, because you will not regret it. It's going to be time well spent.